Preparing for a Java, Microservices and REST APIs at American Express interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do encapsulation, inheritance, polymorphism, and abstraction appear in production Java services? Object-oriented principles help me control change. Encapsulation keeps an account's state behind validated methods, abstraction exposes a payment interface, and polymorphism lets card, bank, or wallet implementations share a contract. I use inheritance sparingly because deep hierarchies become fragile. Composition usually keeps services easier to test. For example, a payment processor can depend on a payment method interface. This design isolates business rules, supports extension, and keeps regulated transaction behavior explicit and auditable. While answering, define each principle, connect it to maintainable service design, explain composition versus inheritance, and use a realistic payments or customer profile example without over-engineering the object model. Question 2. What is the difference between an interface and an abstract class in modern Java, and when would you choose each? I choose an interface when I need a capability or contract that unrelated classes can implement, such as payment validator or fraud rule. An abstract class fits when implementations share protected state, lifecycle behavior, or substantial code. Java allows default interface methods, but I still avoid using them to hide complex behavior. In microservices, interfaces are especially useful at dependency boundaries because mocks and alternate implementations can be substituted without changing business logic. Make sure to cover multiple interface implementation, default methods, shared state, constructors, inheritance limits, dependency inversion, and how the choice affects testing and future service evolution. Question 3. How does Java garbage collection work, and how would you investigate high memory usage in a production service? Garbage collection reclaims unreachable objects, typically using young and old generations. I would first confirm symptoms through heap usage, allocation rate, pause time, and container memory metrics. Then I would inspect GC logs and capture a heap dump during a controlled incident, looking for unexpectedly retained collections, caches, or thread local objects. I would fix the retention issue before tuning the collector. Heap sizing must also respect container limits, because native memory can trigger an unexpected restart. In your answer, discuss heap generations, allocation rates, garbage collector pauses, heap dumps, GC logs, metrics, leak patterns, container limits, and safe tuning rather than guessing JVM flags. Question 4. Explain HashMap internals and the consequences of using mutable keys. HashMap uses a keys hash to select a bucket, then compares keys using equals when collisions occur. Modern Java can treeify heavily collided buckets, improving worst-case lookup behavior. The equals and hash code contract is essential. Equal keys must produce equal hashes. I use immutable keys, such as records or carefully designed value objects. If a key changes after insertion, the map may search a different bucket and fail to find an entry that still exists. Be sure to mention hashing, buckets, collisions, equals and hash code consistency, treeification, resizing, immutability, and why mutating a key after insertion makes lookup behavior unreliable. Question 5. When would you use synchronized, volatile, atomic classes, or a concurrent collection? Volatile provides visibility and ordering, but not atomicity for operations like increment. I use it for a stop flag or published configuration. Atomic integer fits independent counters or compare and set updates. Synchronized is appropriate when multiple fields must change consistently because it provides mutual exclusion and visibility. Concurrent HashMap is useful for shared map access without locking the entire structure. I choose the smallest mechanism that preserves invariance, then verify contention with profiling rather than assuming concurrency is free. While answering, distinguish visibility, atomicity, and mutual exclusion. Compare locks with lock-free operations. Include compound actions and practical examples involving counters, flags, caches, and shared queues. Question 6. How would you design a thread-safe idempotent payment operation in Java? I would require a client-generated idempotent key and store it with the request fingerprint, status, and final response. A unique database constraint prevents two concurrent workers from creating separate payments. The transaction records the payment state atomically, while an existing completed key returns the original response. If processing is asynchronous, the API returns a stable operation identifier. I would reject reused keys with different payloads and use expiration carefully, balancing storage cost against replay risk. In your answer, cover idempotent keys, database uniqueness, transaction boundaries, concurrent requests, response replay, timeouts, retries, and avoiding in-memory only deduplication in a distributed deployment. Question 7. How do checked and unchecked exceptions influence error handling in REST microservices? I use checked exceptions sparingly for conditions callers can reasonably recover from, while unchecked exceptions represent programming or infrastructure failures. At the REST boundary, a global exception handler translates domain errors into stable status codes and structured error bodies. It logs correlation identifiers and diagnostic details internally, never card data or stack traces. I also classify failures as retriable or permanent, because returning a generic 500 response can cause dangerous retries in payment workflows. Make sure to cover domain versus infrastructure failures, exception translation, global handlers, stable error contracts, logging context, retriability, and avoiding sensitive details in client-facing responses. Question 8. What makes a Spring Boot microservice production ready for an American Express-like environment? Production readiness means more than starting the application. I would externalize configuration, load secrets from a managed vault, expose liveness and readiness probes, and publish latency, error, saturation, and business metrics. Structured logs would include correlation IDs while masking sensitive cardholder data. I would add graceful shutdown, timeouts, resilience policies, contract tests, and OpenAPI documentation. Deployment should also include vulnerability scanning, least privilege access, auditability, and rollback procedures for safely handling customer-impacting releases. Be sure to mention externalized configuration, health probes, metrics, tracing, secure secrets, graceful shutdown, resilience policies, API documentation, testing, and compliance-sensitive logging. Question 9. How would you define REST resources and HTTP methods for a payment API? I would model payments as resources, for example post payments to create one and get payments, id, to retrieve it. Post is not inherently idempotent, so I would support an idempotent key. Put can replace a known resource, while patch applies partial changes and delete should reflect the domain's allowed lifecycle. Responses need meaningful status codes, validation errors, correlation IDs, and stable schemas. I would version only when compatibility cannot be preserved through additive evolution. In your answer, discuss resource-oriented URLs, method semantics, status codes, idempotency, validation, pagination, optimistic concurrency, versioning, and consistent error responses. Question 10. What is the difference between put and patch, and what mistakes commonly occur when implementing them? Put represents replacement of a resource at a known URI and should be idempotent. Repeating the same request leaves the same state. Patch describes a partial modification, often using JSON merge patch or JSON patch. A common bug is treating omitted and null fields identically, accidentally clearing data. I would validate both the payload and business transition, use conditional requests such as e-tags for concurrency, and expose only fields the domain actually permits clients to change. While answering, explain replacement versus partial modification, idempotency expectations, omitted versus null fields, validation, concurrent updates, and why domain rules may restrict arbitrary resource mutation. Question 11. How would you secure a REST API handling sensitive customer and payment data? I would enforce TLS, validate signed access tokens, and authorize every operation using scopes, roles, and resource ownership rather than authentication alone. Service-to-service traffic may use MTLS, with short-lived credentials and rotation. Inputs require schema and business validation, while rate limits and abuse detection protect availability. I would never log PANs, tokens, or sensitive payloads. Data should be minimized and encrypted at rest. Audit events must be tamper-resistant and access-controlled. Make sure to cover OAuth 2 or MTLS, authorization scopes, TLS, token validation, input validation, rate limiting, secret rotation, masking, audit trails, and PCI-oriented data minimization. Question 12. How do you make REST calls between microservices reliable without creating cascading failures? I start with explicit, short timeouts and propagate a request deadline. Retries are bounded, use exponential backoff with jitter, and apply only to transient failures and idempotent operations. Circuit breakers stop sending traffic to a failing dependency, while bulkheads prevent one downstream from consuming every thread. A fallback might return cached or pending status, but never falsely confirm a payment. Metrics for attempts, latency, open circuits, and dependency errors reveal whether resilience policies help. In your answer, cover connection and read timeouts, bounded retries, exponential backoff with jitter, circuit breakers, bulkheads, fallbacks, deadlines, observability, and idempotent operations. Question 13. When would you choose synchronous REST, asynchronous messaging, or a hybrid workflow for payments? Synchronous REST works when the caller needs an immediate, authoritative result and the dependency can meet the latency target. Messaging is better for long-running fraud checks, settlement, notifications, or burst absorption. A hybrid API can accept a payment, persist it, publish an event through an outbox, and return a pending operation ID. Consumers must be idempotent, and reconciliation must handle duplicates or delayed messages. The right choice depends on business confirmation semantics, not technology preference. Be sure to compare latency, coupling, delivery guarantees, user experience, consistency, retries, duplicate events, reconciliation, and how a hybrid API can return an operation status. Question 14. Explain the saga pattern and how you would handle a failed distributed payment workflow. A saga breaks a distributed workflow into local transactions, each with a compensating action. For a payment, authorization, ledger reservation, and notification might proceed independently. An orchestrator can make sequencing and recovery visible. Choreography reduces central control but can become difficult to reason about. If ledger reservation fails, the saga releases authorization rather than rolling back another database. I persist workflow state, make every command idempotent, and provide reconciliation because compensation can itself fail. While answering, describe local transactions, compensating actions, orchestration versus choreography, state persistence, failure recovery, idempotency, and why compensation is not equivalent to distributed rollback. Question 15. How would you maintain consistency between a service database and published events? Writing a database row and publishing an event separately creates a dual write gap. One operation can succeed while the other fails. I would use a transactional outbox, storing the business change and event in the same database transaction. A relay publishes pending events and marks them afterward, so delivery is usually at least once. Consumers must deduplicate using event IDs and tolerate retries. I would monitor outbox age, publication failures, dead letters, and reconciliation discrepancies. In your answer, discuss the dual write failure, transactional outbox, polling or CDC, delivery semantics, deduplication, ordering, retries, dead letter handling, and monitoring publication lag. Question 16. How do you test a Java REST microservice beyond unit tests? Unit tests validate business rules quickly, especially edge cases and state transitions. Integration tests exercise the real database, serialization, transactions, and security configuration, preferably with disposable infrastructure. Contract tests protect compatibility between service providers and consumers. A smaller number of end-to-end tests verifies critical journeys such as payment authorization. I also test timeouts, duplicate requests, malformed input, and dependency failures. In C, fast tests run first, while performance and broader environment tests run at controlled stages. Make sure to cover unit, integration, contract, component, end-to-end, security, performance, failure injection, test data isolation, and the trade-off between confidence, speed, and maintenance. Question 17. How would you diagnose latency increases in a Java REST service? I would begin with percentile latency, error rate, traffic, and saturation, separating endpoint and dependency behavior. Distributed traces can show whether time is spent in the database, a downstream service, serialization, or thread pool queuing. JVM metrics reveal garbage collection pauses, CPU pressure, and blocked threads. I would correlate the change with deployments, traffic shape, and database plans, then reproduce or canary a fix. I avoid increasing timeouts blindly because that can amplify queuing and resource exhaustion. In your answer, use a hypothesis-driven process involving percentiles, distributed traces, logs, JVM metrics, thread pools, database timings, downstream calls, recent changes, and controlled remediation. Question 18. What API versioning and backward compatibility strategy would you recommend for evolving a public REST API? I prefer additive evolution, optional response fields, new endpoints, and backward-compatible enum handling. Consumers should tolerate unknown fields, while providers should not remove or change the meaning of existing fields unexpectedly. I would publish a deprecation timeline, measure usage through telemetry, communicate migration examples, and contract test important clients. URI or header versioning can support a breaking revision, but versioning does not excuse poor lifecycle management. The goal is stable contracts with an explicit retirement process. Be sure to mention additive changes, tolerant readers, deprecation policy, schema compatibility, consumer communication, telemetry, semantic versioning limits, and when a new major API becomes necessary. Question 19. How would you prevent duplicate charges when clients retry after a timeout? A timeout does not prove that the payment failed. The server may have completed it. I would require an idempotent key, persist it durably with a request fingerprint, and enforce uniqueness at the database boundary. A retry with the same key returns the original result or current processing state, while a different payload is rejected. Clients can query the operation status rather than creating a second charge. External processor references and reconciliation jobs provide an additional safety net. While answering, cover idempotent keys, request fingerprints, durable state, unique constraints, timeout ambiguity, safe retry guidance, status lookup, and reconciliation with external payment processors. Question 20. How would you design a highly available Java microservices platform for card member transactions? I would run stateless Java services across multiple availability zones behind a load balancer, with autoscaling based on meaningful saturation signals. Data stores need replicated, tested failover and clearly defined recovery objectives. Critical transaction paths should fail safely, avoiding duplicate processing, while non-essential features such as recommendations can degrade. Timeouts, circuit breakers, queues, and back pressure protect dependencies. I would continuously test backups, failover, capacity, and incident runbooks, because availability is an operational property, not merely an architecture diagram. In your answer, cover stateless instances, multi-zone deployment, load balancing, database replication, graceful degradation, disaster recovery, observability, capacity planning, consistency requirements, and operational ownership. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.